Okay, so welcome to lecture 16 of our CS2 classes, and I hope that you all can hear me well. And if you do cut off, just let me know, maybe message or something. So we'll try to reschedule the class if the internet doesn't really go well. But revising a bit from the previous lectures, we saw that, we saw something about the moments of compound distribution. So whenever I'm talking about a compound distribution, I know whenever I have my S defined in terms of a variable, random variable, which is continuous, and another random variable which takes discrete values, our S takes compound distribution, and it is named after the distribution of this n guy here, right? So if my n follows Poisson distribution, my S will be compound Poisson distribution, irrespective of whatever distribution is assigned to my X random variable, which denotes the severity of the claims. And we looked at a way to figure out its expectation, which was using the law of iterated expectations and conditioning it upon n. And we got that, it is just the expectation of x times the expectation of n. Then we also had a look at its variance, which isn't quite intuitive, but if you do derive it, you get some formula like this. Then next, we saw its MGF, the derivation of its MGF. And what we saw was we do not have to care about S, because even if we don't know anything about S, but using only the information we know about N and X, we can easily derive the MGF for our S as well, which turns out to be just the MGF of N with this as the parameter. So instead of T, and I now have log of MXT. And then we had a look at another concept, convolution, and an example of Poisson distribution. And then we had a look at sum of compound Poisson distributions. So maybe this isn't it. This was just the time when I took it as Poisson, I guess. Yeah. So this is when we had a look at sum of compound Poisson distributions. So today what we are going to do is, instead of looking at Poisson distributions, let us see what other distribution our random variable n can take. So one such distribution is binomial distribution, which turns out to be an intuitive choice only in the case of life insurance cases. Would anyone like to guess why?
Because there are only two possible outcomes.
Exactly right. So in the life insurance case, we know that for each policy, there can only be one claim or no claim. So we know that there is a binary outcome that we are looking at, and such is the case with the binomial distribution as well. So either the event can be successful or it won't happen and we claim it as unsuccessful, right? So the parameters that we usually have for binomial case is n and p. So I guess you guys would remember theta, and let me just denote the number of successes here by p. So let's say if I say that my n follows binomial distribution, the parameters I'm going to have are n and p, where n denotes the number and p is just the rate of success. So, I mean, the probability that I will observe something that I call as success. Okay, so again, we are going to do the same thing and try to figure out the moments for our compound binomial distribution. And we know it's compound binomial. Why? Because again, I'm assuming that my n follows binomial distribution with the parameters n and p. So do you guys remember the very first step to figure out expectation of S? So even before we try to figure out expectation of S, the best thing is to figure out all the moments of n that we know of, right? Because that is just going to help us to figure out the moments of S later on. So what is my expectation of n here? Anyone? What would be my expectation of n in this case?
N into P.
Exactly, Prajakta. N into P. What about variance? What will be my variance?
N into P into Q.
Exactly, it will be n into p into q. And when I say q, I know that my q is nothing but 1 minus p. So I can maybe write it as this as well, right? Depending on the convenience. So I'll just see what is much more convenient to me. And then I'll decide whether I have to use q or I have to keep it as 1 minus p. So the next thing is MGF. And I guess it's in the table booklet. So the MGF is just Q plus P e raised to T. So instead of Q, I'm going to write 1 minus P here. So I have this is my Q plus P e raised to T. And then all of this thing raised to N. So this is nothing but my Q here. Does this make sense to everyone? So again, be mindful that we haven't yet assumed anything about X. So again, we are going to use the same concept that we used up until now, which will be that so my M1 basically, so my MK will denote expectation of X raised to K here. So my M1 is expectation of X, my M2 will be expectation of X square, and so on. So now if I have to figure out expectation of S, what will be? So again, I'm defining my S as summation I going from 1 to n of Xi's, right? Where my n follows binomial NP. So if I have to figure out my expectation of S, I do remember from my previous calculations that it is nothing but expectation of n times expectation of X, right? So expectation of n is NP here. So I'll have NP, and instead of expectation of X, I'm just gonna write M1 here. Does this make sense to everyone? Do you guys remember this?
Yes, ma'am.
Yes, ma'am.
Right?
Yes, ma'am.
Okay. And next up, we want to look at the variance of S. So the formula for variance of S, if you substitute, it was something like expectation of N times the variance of X. So variance would be expectation of X squared minus expectation of X the whole square. And then you added on the variance of N, which will be NP 1 minus P, and then you multiply it by expectation of X the whole square. So this will be the variance of S. And the last thing that we have to figure out is MGF for S. So what was the formula? It was something like Mn, and instead of T, you had log of mxt, right? So again, here you don't know the value of mxt. So what we will do is, instead of this T, we are just going to substitute log mxt. So you see this T and this log will cancel each other out. So what you will be left with is 1 minus P plus P times mxt. And all of these raised to N, which you should never forget about. So does this make sense to everyone? And okay, so now this is all you would probably need anytime. But there is one more thing that is given in the books, and I think we should go through the derivation itself in the class, is to figure out the skewness of this compound binomial distribution. So again, reminding ourselves to figure out the skewness, what do we have to do? Does anyone remember? If I have to figure out the skewness, what is it that I use apart from NGF?
Differentiate,
Yeah,
3 times.
exactly. Yeah, so I guess Ananya and Vanshita said correctly. We'll have to differentiate the CGF thrice and then evaluate it at 0, right? So let us try to do that. But again, what is our CGF? It's nothing but the log of MGF, right? So instead, what we are going to do is to figure out the skewness. What we have to look at is the differentiation 3 times of log of MGF, NGF of not of n, not of x, but of s, right? Because we are trying to figure out skewness of s here, right? So we have to basically differentiate this log of mst thrice with respect to t, right? Does this make sense to everyone? So now reminding ourselves of what was our log of MST, if I'm taking log of, let's say if I'm taking log of a raised to b, I know that I can rewrite this as b times log of a, right? So here if you see my n is b and a is the whole thing that I have in the brackets here. So what will I have here? I'll just have d3 upon dt cube of n times 1 minus p plus p mxt. Does this make sense to everyone?
And n log of 1 minus.
Oh yeah, it will be log, right? Yeah, should be for the log there. Yeah, so it will be n times log of this whole thing. Yeah. Okay, so now we have to muster enough strength and courage to derivate this thing thrice. So let us try to do it. Would anyone want to guide me through this? So again, so let us say, for convenience, what I'm going to do is, because I'm differentiating with respect to t, I'm going to save myself some time by not writing 1 minus p, but substituting 1 minus p as q. Can I do that? Because it anyways does not depend on t. So I'm just going to write it as q, right? And I know that my p plus q is 1. This is a fact. Okay. So now if I have to differentiate this thing, n will come as it is, right? And I know if I have log here, so okay, we are just differentiating it once. So again, I have to differentiate it twice, but let us see what happens now. So if I have log of x and if I'm differentiating it, I know the bracket term will come in the denominator as it is. So it will be this here in the denominator, and then I will have to differentiate this numerator with respect to t. So differentiation of q with respect to t will be what?
0.
Exactly. And differentiation of this thing with respect to t will be, let's say p, and I don't know anything about this, so I'm just going to write m prime xt. Okay, so prime ones represent differentiation ones with respect to t. Okay, does this make sense to everyone up until now?
Yes, ma'am.
All right, so now we'll try to differentiate again the term within the bracket once. So I will only write d upon dt outside. And what should I have now? So if we were to have a careful look at this expression, which is within the brackets, I see that the thing that I'm differentiating with respect to t appears not only in the numerator, but also in the denominator, right? So I will either have to use u by v rule, but again, I personally do not prefer u by v rule. So what I'm going to do is, I'm just going to rewrite this term in the bracket as this thing times q plus p mxt raised to minus 1. Is this fine with you guys? Again, if you want to follow me in the class, you can follow me in the class, or you can choose to do the derivation by yourself as well, if you just want to practice. So again, now if we now we'll just have to use u by v rule, u times v rule. So let us differentiate this thing first. So I'll have np as it is. These guys do not depend on t, and this does. So I'll have m double prime x t, and this will be as it is. So I'll have q plus p mxt inverse, right? So this is going to stay as it is. And next up I'll have plus. Now this will be as it is, np m prime x of t. And now I have to differentiate this thing. So I'll have to use chain rule because I have this minus 1 first. So what I will have is minus 1 here, q plus p mxt raised to minus 1, which will be minus 2, right? And then I'll have to differentiate this thing. So differentiation of q with respect to t is again 0. And differentiation of this guy with respect to t will be p times m prime of xt, right? So let us just try to rewrite this once again nicely. So what all do we have? We have np m double prime xt q plus p mxt inverse. This minus will come outside. So I'm writing a minus here. And I have a p here and a p here. So I'm going to write n p square. And I have m prime of xt, m prime of xt. So m prime of xt square and this thing as it is. So it will just be q plus p mxt raised to minus 2. And I'll just complete this bracket that I started off with. Hello, am I audible?
Yes, ma'am.
Yeah, I'm sorry I received a call, so I'm working also with my research and we have a deadline soon. But yeah, all right. So we were supposed to differentiate this thing once again, right? All right, so we have this thing here. And now again, we have to, we can again use the UV rule again and again to do the same thing. And maybe do we find some commonalities? Maybe not now. So what can we do now? I'll just, use UV rule again. So I have NP here and I'll differentiate this guy first. So I'll have M thrice xt and this will remain as it is. So, this is the last step. So I'm just going to write it downstairs, mxt. And now I'll have plus. Now I'm going to keep this thing as it is. So NP M double prime xt. And now I'm going to differentiate this guy. So what will this be? -1. And this whole thing will be raised to -2. So I'll have q plus p mxt raised to 2, right? And again, now I have to differentiate this thing. So I'll have p square and m prime of xt. Is this clear to everyone? So this pertains to this part here. And for the next part, we are going to write it now. So I have minus, and I'm just going to put a bigger bracket here. And I can again use the UV rule. So maybe this is not the most efficient way to do. Maybe you can find some commonalities here, like you have NP square and NP square here as well. But yeah, depending on how and what you guys prefer. So again, let us differentiate this guy first. So we'll have to use chain rule again because this is m prime of xt square. So I'm going to write 2 here and m prime of xt. And then I'll have to differentiate this guy, right? So it will be m double prime of xt. And I'll write this guy as it is. So it will just go in the denominator, q plus p mxt square, right? Because this was as it is. And now I'm going to add this and keep this term as it is. So this will be what? Np square m double prime of xt. Sorry, it's just a single prime. So what we have is m single prime of xt squared. So this is as it is. And I'll have to differentiate this thing now. So -2 will come outside. So -2 upon this thing with a -1 here. So what I will have is q plus p mxt raised to 3. And what will I have? Again p. So this will become p cube. And again m prime of xt. So this will also become cube again. Does this make sense to everyone? Were you guys able to follow through what I just did?
Yes, ma'am.
Everyone else?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. So now what do we have to do is just see the commonalities and then substitute in the 0, right? So again, if we have mxt, so for all the times we have mxt here, if I substitute 0 in mxt, let us see what happens. Do you guys remember what happened the last time we substituted? So if I have mx of 0, what will it be? It will just be expectation of e raised to x 1, exactly, right? So every time I put here 1, what do I have in the denominator? Q plus p. And what is q plus p? 1, right? So this is going to be 1. This square is also going to be 1. This square is also going to be 1. And this cube is also going to be 1, right? So all the terms in the denominator go away. So we do not have to care about those terms now. So what are we left with? So what I'm going to do is maybe just write a note somewhere. here. Therefore, Q plus PMX 0 is 1, right? And this happens here. Okay, so we have that now. And now what we can do is, so basically here we are substituting T equals to 0. All right, so I'm gonna write NP as it is. We have NP, and instead of M triple prime of XT, what I'm gonna write it as, I'm just gonna write it in shortcut terms, which will be M3. So this basically denotes the value of this thing at T equals to 0. Okay, and what do we have next? We have plus NP square, and what will this be? Okay, we have a minus here as well. So let us take into account that as well. So we have minus NP square and M double prime XT. So that would just be M2, and this will be M1. Does this make sense to everyone? So this here is again going to be 1, right? Because Q plus P times 1 squared, Q plus P is 1, 1 square is going to be 1. So now again I have a minus. And what do I have here? I have 2n P square M prime XT, which is M1, and M double prime, which is M2. So if you have a look, this is NP square, M2, M1, M2, M1, right? Minus 1, minus 2. So you can maybe combine this, and what you will have is minus 3. Okay, and then the last time we have a minus here and we have a minus here. So that will become a plus, and we have 2 here, and here we have NP cube. And what do we have here? M prime of XT cube. So remember, M prime of XT is M1, and this is what we are going to cube. So this is not going to be M3, it's just going to be M1 cube. And now because we know that we can combine these two, the simple answer I have for my skewness of compound binomial distribution is something like this. So it's minus 1, minus 2, minus 3 NP square M1, M2 plus 2n P cube M1 cube. Does anyone have any doubts with this derivation? Maybe not now, but if you try to do it by yourself, I think you guys will realize certain mistakes that are bound to happen if you try to do this sometimes. So, is this clear to everyone?
Yes, ma'am.
Yes.
Do you guys need a minute
ma'am.
or two to go through it? It's clear to everyone else as well? I think it just looks monstrous, but if you go through it slowly, and personally, I do not like U upon V rule, so I always try to use U times V rule, even though it can make sometimes things lengthier, but at least it's clear to me. So again, remember, we use the fact that our MX0 is just 1, and we make this whole numerator denominator thing converted to just the numerators, right? Because all the denominators that we have go to 1. So that really doesn't matter if you don't write them. And what you're left with is this. So again, this is the derivation for skewness of S. And again, you can derive the formula for the coefficient of skewness as well, which would be what? Just the formula for skewness upon. Does anyone remember the formula for coefficient of skewness?
Variance upon variance raised to 1.5.
Exactly, right? It will be upon variance raised to 1.5. So I want you all to have a look at the coefficient of skewness formula for the compound binomial distribution and tell me what is its value. So whenever we looked at compound Poisson distribution, we saw that it is always positively skewed, right? So the coefficient of skewness ka value was positive, that was greater than 0. So I want you all to figure out the coefficient of skewness for compound binomial Okay, and tell me its value. So then this would be your homework for today. I mean, I don't think it's going to take much time actually, because we have already derived this formula and you guys already know the variance as well, which is this, right? And you guys do know that P and Q always take positive values. It can never go negative. So do take that into account as well. Okay, so this was about the times when we have our n following binomial distribution. So whenever I'm saying that, my n is a binomial distribution, I know that I was looking mostly at I was looking at the life insurance cases. But again, that's not always the case. So we can also have our n following we can also have our n following negative binomial distribution. And if that is the case, our S will be compound negative binomial distribution. So these are just, the basic general distributions that we have of discrete type, which we can assort to N, which will render us different type of distributions for our S. And then what we can do is we can just check with the data that we have and the properties of that data set. So the very first property that I will, say out loud that this data set is or has to be a post-one data set will be if its expectation and variance is the same. So let's say you encounter some data and you calculate its mean and you calculate its variance. And if that turns out to be the same on an average, then the very first thing that will come to your mind is that, okay, maybe this could follow post-one distribution. But what if that is not the case? And again, what if you are not looking at life insurance cases? Then the next option that you would usually have a look at is negative binomial distribution. And what happens with the negative binomial distribution is that here the variance will exceed the value of mean. So variance being equal to mean is normally, not that plausible case as well. But again, there will be some significant difference. So it's not the case that, even if the mean and the variance differ by 1, you're going to say that, okay, they aren't equal, so this cannot be possible. No, that won't be the case, because there will be some significant difference that you have to check. कि अगर difference इससे ज़्यादा बड़ा रहेगा, तब we know कि ये पक्का पहुंचवा नहीं है. But अगर difference इससे कम है, then it may or may not be Poisson distribution, right? So again, I think there will be a similar derivation for the coefficient of skewness as well for the compound negative binomial distribution, which I will not be doing in the class and which I would suggest for you all to try it out by yourself. And do let me know if you again encounter any doubts. So the very first thing that comes to my mind whenever I'm talking about negative binomial distribution is we have two types of negative binomial distribution, right? One is a type 1 and the other is a type 2. So do you guys remember what is what are the cases when I look for negative binomial distribution? Can anyone summarize negative binomial distribution for me? What do you guys remember of negative binomial distribution? What does it say? Anyone?
Like for type 1, it is like the number of trials that is required for the case success. And for type 2, it is like number of failures before the case success. So we are finding the probability that the nth trial would be the case success or something like that.
Yeah, exactly. So what we are generally looking at is a number of fixed successes, right? And then we look at the chance of that particular thing happening. So the very first thing you have to do is we cannot take type 1 into consideration, because what it assumes is that there will be at least k number of claims incurred. But what we have a look at is that the claims are independent and they can occur and they cannot occur. I mean, there is no fixed number that number of claims should always exceed. So type 1 doesn't really suit well to our purposes. So what we use is a type 2 version, which is given on the page number 9 of your table booklet for the negative binomial distribution case, right? So if I just write its probability distribution, it is something like, so again, remember, I'm going to write this for n. So this will be the probability that my n takes some value, which is small n, and I can summarize this as k plus n minus 1 n p raised to k q raised to n, right? And here n takes values from 0, 1, 2, and so on, so right? So again, this is, we are looking at compound negative binomial distribution. So again, I mean, you would do the same thing over and over again for this thing. It's no different. And the parameters which you will have here is, because it follows negative binomial, what are the parameters? We have n and we have k here, right? So our n would represent the number of claims and our k would represent the success, the number of fixed successes that we want. So again, reminding ourselves, our claims have to be independent, and if we are figuring out, oh sorry, we don't have n right here in the negative binomial case. What are the parameters of negative binomial? Anyone? It's not n and k. What is it? It's k and p, right? So n is the random variables value here. What is k? K is the number of successes that we have, and p is the probability that you will observe a success. So here, what is our success? The success is a claim occurring. So maybe it is incurring a loss, but that is what we are looking for. So that is how we define our successes here. So p would be the probability of observing a particular claim. All right. And again here, because k is measuring the number of successes, which is the number of claims that do incur, we will have this condition that k has to be greater than 0. And because p and q are looking at the successes and the failures of claims incurring and not incurring respectively, they will add up to 1 always, right? Either a claim will be incurred or it won't be incurred. So that's all we have. And again, you would do the same thing basically. You will see expectation of n from the table booklets, variance of n from the table booklets, MGF of n from the table booklet, and substitute in the stuff and get the skewness formula as well. So I would say, okay, and also there is, I don't know if you guys know about IBNR. Has any one of you heard this term IBNR before? Anyone? So I'm actually talking about this thing, IBNR. Has anyone heard of this before? No? Yes. Am I audible?
Yes, ma'am.
Yeah, okay. So have you heard of IBNR or not? So IBNR is actually just a short form for incurred but not reported type of claims. So sometimes what happens is a claim has been incurred and the insurance company is aware that this claim is going to incur and this is going to be written in the books, but it hasn't just been written yet. And that could be because of, the dispute between the policyholder and the insurance company on the exact claim amount or the exact loss. And it might take some time to figure out the exact figure which is to be traded among the parties, right? So what can happen is, we know that in the balance sheets of the companies, they will write off some claims as incurred but not reported. So they'll have an estimate of the loss. So when I'm saying that my P plus Q is equal to 1, what I'm saying is that I can either observe a success or a failure. So I'm essentially saying that there is no such case where I have incurred a claim but I haven't reported it. So I'm in a way assuming that my reporting of claims is instantaneously, and I write it in the books as and when it is incurred to me. So this is basically a hypothetical assumption on which these models are based. So again, we have to be mindful that this won't happen in the actual scenario, but this is what we start off with. And again, you will have complex versions of these models once you study these basic models, but I guess that we don't have in this subject. So, okay. So I guess, is it okay if I tell you guys to figure out the skewness of the compound negative binomial distribution as well? I mean, you don't have to necessarily send that to me and show it, but just do it for your sake. And again, they won't necessarily ask you to derive this in the exam, but I think it's just a good practice of trying to differentiate stuff, because sometimes we make mistakes and it's good. So you also have the answers in your books to check from. And again, if you do have any doubts in any of the steps, do let me know. So, and again, you should try to figure out the coefficient of skewness as well and try to see if you can figure out its value or not. So that would depend on what answer you get and what are the parameter values here. So the parameters here will be P greater than 0, K greater than 0, and N is also greater than 0, right? So whatever you have, you should decide what will be the value of the coefficient of skewness as well. Does this make sense to everyone? Does anyone have any doubts up for whatever we have studied up until now? Anyone? Any doubts? Because now I'm going to let's just solve a question actually together. So this is just the theory parts. I've skipped it, and we'll try to solve a question together. And then I guess there are some pretty important concepts in that one question. And yeah, let me just open the book. Can you guys see the book? Yeah, right. Okay, so let us try to do this exam style question. And so would anyone want to volunteer to read the question for me and for everyone else? Yeah. Okay, so maybe I guess we should just solve the question, and what I can do is, okay, so what is the question asking of us? We have the aggregate claim amount from a portfolio, and they say that it has a compound negative binomial distribution. So the very first thing that you should notice is that they have said aggregate claim amount, not claim amount, right? Because claim amount would follow some continuous distribution. And whenever they're talking about aggregate claim amount, what do they mean? They mean S. So this is my aggregate claim amount. So my aggregate claim amount is S, which has a compound negative binomial distribution. So what do I infer? I know that my N has a negative binomial distribution, because that is the only times when I will observe my S to be a compound negative binomial distribution. So the very first part of this question asks us to show that, okay, we have already done this, right? Do you guys remember? We have already shown this, that our MST is just Mn log of MXT. Maybe I can go through that. I guess it was pretty much. Yeah, so this was expectation, variance, and then we did this MGF, right? So this is the answer to your first part of the question, which again, I don't think is likely to come up, especially given the online exams. So let us directly skip to the second part of the question, which is very interesting and has something to do with what we just studied. Okay. Oops. Yeah. So would anyone want to summarize the information I have on the board for the second part of this question? Yeah, so it's here. Or should I take names? So Isha, can you help me with this?
Hello.
Yeah, we can hear you.
Yeah, so it says that if n has type 2 negative binomial distribution with k equal to 2 and p equal to 0.9, and x has gamma distribution with alpha equal to 10 and lambda equal to 0.1, determine an expression for MST.
Yeah, so would you all want to try this for yourself? I guess we have done this ample times, right? So I want you all to now try it in your notebooks and do send me the pictures on WhatsApp. So for those who have already finished the part 2, you can try and move on to the part 3 as well. Does anyone not have table booklets with them? Because then I guess it would be a bit tedious to figure out the answer. So do let me know if you don't have the table booklet with you. I can maybe send the pictures in the group.
Ma'am, I'm having trouble finding out the MST. Can you please help me?
MST. So what all have you tried up until now?
So since MST will need like the formula is mn of log of mxt, I found out the mnt and mxt individually.
Yeah. So let us try to do it on the board now, okay? For everyone else as well, to whom I have mentioned some corrections in the WhatsApp. So do have a look on the board right now. So if I have to figure out MST, what do I have to do? The simple formula is Mn log of mxt, right? So the very first thing that comes to our mind is that we should try to figure out what is our mxt, right? So let us try to do that. So we do know that my x follows gamma distribution, right? So if my x follows gamma distribution, now let us see what is its mxt. So I go to page number 12 in your table booklets, and you have the values for t and lambda respectively, right? So if you have a look, and if you try to write the mxt, what will it be, Isha?
Yeah, the mxt, right?
Yeah.
So it will be 1 minus t by lambda raised to the whole raised to minus alpha.
So what is my lambda here and what is my alpha here?
The lambda is 0.1 and alpha is 10.
Sorry about, I don't know, it's working weird. But you do understand, this is minus 10, all right? Yeah. So what is this? This is your mxt. Can you simplify it further? So because we have 0.1 here, I can just
Yeah, it
multiply
will
it by,
become 10.
yeah. So what will it become? It will become 1 minus 10t raised to minus 10, right?
Yes.
Okay. So that is done. Now the next thing that we should do is let us figure out m and t. So what does my n follow?
Negative binomial.
And what kind of negative binomial? Is it type 1 or type 2?
It's type 2, right?
Yeah, it is type 2. So can you dictate the MGF for it? Don't dictate to me what's there in the books, but use these values and tell me what should I write here.
So it will be 0.9
Yes.
upon 1 minus 0.1 into e raised to t, the whole
Yes.
raised to 2.
The whole raised to 2.
Yeah.
Right? Okay. So now what do I have to do? Instead of this t, I have to substitute log of mxt. Right? So instead of this t here, inside my bracket for my mn, what do I have? Log of mxt. So what I'm
So
going
the
to,
e and log will cancel out and it will just become 0.1 t.
will become 0.1 t or something else.
Like the e raised to t will become e raised to log t, right?
Will it become e raised to log t? So instead of t, what do I have? E raised to log of mxt.
Yeah, alright.
What will this become? mxt, not t,
Yeah,
right?
mxt.
And what is my mxt? It's this thing right here. So 1 minus 10t raised to minus 10 and all of this raised to 2. Does this make sense to everyone? Isha?
Yes, ma'am, got it.
Got it? So what was the thing where you got confused with this actually?
So I wasn't understanding the, like, how do I put in the log mxt part. So I didn't realize that I would just have to put it in place of t.
Yeah, so again, so I mean, I do understand that it looks a bit confusing here, but it's actually the parameters. So I think that is why this question is really important. But again, yeah, it's good. So now you know, right? Perfect. And about others as well, you should not only try to use the information that you're given directly, but also try to infer what all you can calculate. So we were given information only about P here, but we know that P and Q add up to 1. So we could easily figure out the value of Q here, which would be 0.1. Perfect. So, okay. I think now we should try to move on to the part. Okay. Before that, does anyone have any doubts with this part?
No, I didn't get that last thing. I mean, the final answer.
This?
I mean, I understood what you did, but I didn't get. Yeah, I think.
Yeah. So what exactly are you confused with?
I mean, it is e raised to 1 minus. I mean, it is e raised to log of 1 minus 10t raised to minus t, right?
Yeah. So if we have e raised to
Okay, so
log of
log and
mx.
e that got cancelled out.
Yeah, exactly. So it just became mxt here. I've used this fact.
Yeah.
All right. Any other doubts? Anyone else? Okay, so now I want you all to try and figure out the third part. So you have to calculate the mean and variance for S here. So again, use the information that S is this thing here, and our N follows the negative binomial and our X follows gamma distribution with such and such parameters. So what will be the mean and the variance for S here? That is what we need to figure out now. And where? Are you trying the expectation and variance of S?
Yes, ma'am. I have sent you the photos.
Okay, yeah, I just got. Prajakta, what about you?
Ma'am, I'm trying. I did some mistakes, so yeah, I'm figuring that out.
Okay, chalega, all right. Prajakta? Did you figure out your mistake? Otherwise, you can send me the picture and I'll just have a look.
Yes, ma'am, I sent you the picture.
Okay, I'll have a look. Okay, so Prajakta, your expectations answer is correct. It is into 22.222, but I would want you to check your variance का answer एक बार में. So you haven't explicitly, mentioned the values. You have directly written the answer. So what you should do is instead substitute in the values as well, right? And
Yeah, like I used calculator, so I directly substituted values in the calculator.
Yeah. So maybe you should try to figure out the values. So what was your value for M1?
M1
Again,
is alpha by lambda. That would be 100.
yeah, exactly. That's correct. And what is your value for M2?
Wait, I'll have to calculate that.
Yeah, just figure that out.
I'm getting M2 is minus 9,000. That's where I know like I'm doing something wrong.
Yeah, so what is the variance for X?
Variance is,
Alpha upon lambda square, right?
yeah,
And what is your lambda here? 0.1. What would be its square?
1,000.
Will it be 1000? So your alpha is, okay, maybe I'm not sharing, right? So your alpha value is 10 and you have 0.1 square in the denominator. So you will get variance of X value as 1000, right? And then what do you have to do? You have to use variance of X, right? So you directly substitute 1000 here and expectation of N you have and variance of N you have from these calculations.
Oh, okay, yeah, okay. I figured out what I am doing wrong.
Figured it out? All
Yeah.
right. Yeah. So this should be your final answer.
Yes, ma'am, got it.
Got it? Very well. So try to do the next part of the question now. Which would be this. Andrea, can you hear me? I'm just trying to download your picture.
Yes,
I guess the
ma'am.
internet connectivity is going crazy again. So, Prajakta, are you trying to do this B part?
Yes, ma'am, I'm just sending you the picture.
All right. Ananya, will it be raised to 100? Your ms of t is raising to 100, right? So your mst already has some power, which is 2.
Oh, right.
Yeah. So it will be 200. Yeah, that's it.
200, yeah.
Yeah, you can move to the B part as well. I guess my internet is weird. Maybe you guys can hear me on Zoom, but WhatsApp is not working.
And for the fourth B part,
Yes.
they have said using normal approximation. So to find expectation and variance, we'll have to differentiate the MTT, right? So like it will be difficult, right?
Do you really have to differentiate MT? Check. So
So
remember the way we try to figure out the expectation for S. What is S? S is the summation of x's, right? Where x follows some gamma distribution and our S follows negative compound negative binomial distribution. So now what do we have? So in class, remember we looked at the sum of compound Poisson distributions. Similarly, here we have compound negative binomial distribution and we are looking at sums for those here. But there is one difference. Here they are saying that the insurer in fact has 100 identical and independent portfolios, right? So we know that all of these S's are not only independent, but they are identical as well. So if you have to, let's say, figure out expectation of T, what can you do? You can simply replace T with all of these S's, right? And then use the fact that they're identical as well as independent. And then I think it's easier. And you
in
will
place
have
of
to,
T, we can just write 100 into S.
yeah, not exactly that, because so it's like, I think the best way to do that would be something like this. So if you have expectation of T, you can write it as expectation of S1 plus S2 up until S100. And then you can rewrite this as expectation of S1 plus expectation of S100, right? Because these are independent. And now because these are identical as well, you say that this would just be 100 times expectation of S1. And that will be 2 to 2 to whatever you have. So your T won't be expected. If you write T as 100 times S, it would defy what you have here, right? It would contradict. So what you can write is expectation of T is 100 times expectation of S. This is correct, but this is not. Do you understand the difference?
Yes, ma'am, got it.
Okay.
Ma'am, then can we do the same thing for variance, like 100 square variance of S? Or no?
Who is that? Was that Andrea? Andrea? Very good question, actually. So I was waiting for someone to get stuck over there. So let us see. So when I have to figure out the variance of t, what can I write this as? I will write it as variance of S1 plus S2 up until S100. So I want everyone to look at what I'm writing and leave whatever you are trying to solve. Even if you have solved this previously, please have a look here. This is important. So what Anvaya said is that this should be 100 square variance of S. So for those of you who have already solved this sum, I want you guys to refute Anvaya and say, why can you not write it as such?
The same reason we told for the expected value, that t is not equal to 100s, but we can't write t equal to 100s. But we can write expected value of t as 100 into expected value of x. The same reason applies here as well.
Exactly right. So what we will do here is, instead of jumping to the conclusion, let us go step by step. So we have variance of S1 plus S2 till S100, right? And now we will use the fact that these guys are independent. And what we will do is, we will write variance of S1 plus variance of S2. So there will be no covariance term because these are independent. All the covariance terms will be 0. So you will be left with only the terms which have variance. And now you will use the fact that all of these are identical. So you can write this as 100 times variance of any of this. So let's say you write S1. So it is indeed 100 times the variance of S1, not 100 square times the variance of S. So this is the difference that we will be looking at in this part actually here. I'll explain that once again. But till then, do you understand this part? And why can't we do this? Anvaya? And
Yes,
rest
ma'am.
of you guys as well?
What Vanshika said, actually.
Okay, so let us take another example.
Please repeat what Vanshika said. I cannot hear you.
Oh, you couldn't hear her. Okay, forget about her. I'll try to explain with some new example. So what she said actually was the same reason why we couldn't write t as 100 times s. I mean, she is indeed correct, but I think I can maybe try and explain it a bit better. So see, let's say if you have let's say if you're trying to bet on something. So what you can do is, you can have one bet. So you have 100 rupees. Okay. You have 100 rupees with you. And what you can do is, you can either put all of that 100 rupee in one bet, or you can choose to buy 100 different bets and put one rupee in all of those bets. So in the very first case, where you're putting all of your 100 rupee in one bet, what are the outcomes that you can have? Either you can get all of your money back. So I'm assuming that there is 0% return. I mean, this is a not profit only loss kind of a thing, but it's easier for explain point of view. So if you win the bet, you get all your 100 back. But if you lose all of your 100 rupees, right? And what will happen in the second case? You have different bets. So what can happen is, you can win one bet, but you can lose another. You can win two and you can lose three, and maybe there will be a nice combination because you have invested in 100 different bets, right? So in half of those you win, in half of those you lose, or in 60% of the bets you win and in 40% of the bets you lose. So the number that you will have with you will vary from 0 till 100. Sorry, it can vary from minus 100 till 100, right? Depending on the way it's distributed. So what happened in first bet was, you put all of your money into one bet. And that is the case where you will have this kind of a scenario where this S1, S2, S100 do not exist. there only exists one S, and you have put in all of your money in one bet only. And that is when the variance will have 100 square times the variance of S. But here what's happening is you have different bets, but they are all identical. You have invested one in each of the bets. So you know if you lose, you will lose -1. And if you win, you will get 1. Right? So this is what's happening here. So all of these bets are identically distributed, and which is why the variance is the same. So you use first the fact that these are independent, and then you write them separately, and then you use the fact that these are identically distributed, and so you have these variances all equal to each another. So 100 times variance of S1. So again, I mean, here, see, if you see, they do not mention identically or independently distributed as well, right? So they are identical. They are actually, I mean, you cannot differentiate between S1 and S2 and S3. They are all the same, but they are different. You know that S1 is not S2 and S2 is not S3. So these are 100 different bets that you are investing in. And over here, if you are trying to look at this is just one bet where you're investing all of your money. Does this make it a bit clearer? Or is there still some confusion?
No, ma'am, I got it.
Got it? All right. So I hope each one of you has figured out the variance at least. Yeah, so I guess MGF is done. Expectation and variance, I'll give you guys 2 minutes to do that. Is everyone done with the expectation and the variance of T part?
Yes, ma'am.
Okay, so I guess the same thing you have to do again, right? The thing that you did in part B for the third. So actually to get the value of 0.1%, you can also have a look at page number 162 of your table booklet, and it directly gives you the value 3.0902. So you can save some time. Okay, so I guess everyone has finished up until 4th B part. So did anyone try to think for the C part of fourth? So for third B, you have some answer. And for fourth B, you have some answer, right? Maybe let us just go directly to the answers page. I guess it's yeah. So for third B part, we see that the answer we have is 182.54, and for fourth B part, we have 383,825. So what would you guys have to say about this? Did anyone try to think about what kind of a comment would you like to put there? Anyone?
Can we say that the one regarding T, like the value, it is much greater because it is like an aggregate of S?
Yeah, that's one thing. But again, what do you have to compare? Is it okay to compare one S and a combination of S's? I mean, even if it were not this, it would, I mean, even if it were something else, if you compare one S and the combinations of multiple, let's say 100 S's, then the same result will hold true, right? So what else? What about others? What do you all think? So it is actually related to what I explained to Anvaya regarding the variance bet of T. So remember what we did in here, this is for S, this is for a single S, right? And here we have T, which is summation of S's, which goes on till 100. So what we are trying to compare now for a comment regarding this part and that part is not exactly this S and this T, because we know that this is just one part of this and we are adding hundreds of this. So it's damn clear that, you know, this variance for this guy is going to be higher. But the sensible thing to compare would be hundreds of S and 100 different S's. So basically what will happen is, if you figure out the hundreds of similar S's, what you will get is the variance would be 18254, right? And here what would it be? It will just be, it is 3825. So you know that you have invested in 100 different portfolios, and which is why you get the variance, which is way smaller than if you invest all of your 100 rupees within one portfolio. Then your variance would be something like 18,254. So that is what they are trying to say. Basically, it's the idiom that says, you know, don't put all your eggs in one basket. So what happens is, generally whenever you're forming a portfolio, and let's say if you have number of policies within a portfolio, what you would want to do is, maybe for the number of portfolios as well in a bunch that you're trying to get, or maybe number of policies within a portfolio. So let's say if you're looking at the number of policies within a portfolio, what you would want to do is try to have a variety so that let's say if one of the stocks go really bad, the other stocks performance could offset. So again, we are conditioning that other stocks will perform good. And that is where the stock which went really bad, the loss from that stock would be offsetted by the ones which will perform good, and you will get some stability within your portfolio. But let's say if instead you only invest in one bet, then either you will win or you lose. So you either have all the 100 or you do not have the 100, right? So the variance is huge. But in the kind of bet where you are investing 100 rupees, not in one bet, but one rupee in 100 different bets, you know that the variance is small because there is a 50-50 chance of each one of them winning and each one of them losing. So it's that, and that is where central limit theorem also comes into picture. So if you read what they have to say about this, is that, as the number of portfolios increase, bad experience in some of the portfolios will be offset by better experience in others. So this is what they mean when I say that, let's say if S1 goes bad and if S100 goes really great, then you won't be suffering the loss of S1. I mean, you won't be either gaining the huge gains of S100, but you will have a stable portfolio. You won't go bankrupt. So there is again a risk and a return trade-off always. So the higher the return you want, the higher risk you have to take. But again, if you don't want a higher risk, then you have to compensate with some of the return. Because let's say if you are not willing to take a higher risk, let's say if you are a risk-averse investor, then what you would do is you would invest in a variety of options, right? And you would try to hedge your one portfolio with another portfolio where you might invest in, the opposite going stocks, or let's say any strategy that you might want to employ. So it's just saying that the variance, if you compare for hundreds of this S versus different S's, different 100 S's, then the variance in this case would be much, much higher than the variance in this case. So the end line is that pooling of similar risks reduces the overall variance. So basically what you're trying to do is, here you're pooling them together, but here you're just investing in one of them. And that is what is happening here basically. Does this make sense to everyone? Any doubts, any questions regarding this whole sum that we just did? Am I audible to you guys? Yeah. Okay, so any queries regarding this particular question? Yes or no?
No, ma'am.
No, ma'am.
What? Okay, thank you. What about others?
No, ma'am.
So that we can start with the next topic for today. So up until now, what we had a look at was compound distributions only when the insurance company was in picture, right? But we have already seen that sometimes insurance company also tries to insure their claims with a reinsurance company. So now we will try to see how to analyze these compound distributions when we have reinsurance in picture. So let me start a new. Okay, yeah. Share my screen. So my screen is visible, right? Yeah. So again, to remind ourselves, we have our S, which is what? Which is just sum of the claim amounts, which go up until n, and we do not necessarily know the value of n. So remember, we are looking at the collective risk model. We haven't yet looked at the individual risk model, and we'll have a look at that maybe tomorrow. So what we have here now is, let us say that there is reinsurance treaty in place. Then we know that we denote the amount which will be paid by the ceding company, the insurance company, the direct insurance company, by Y, right? And the reinsurance companies by Z. So what I'm going to write is, I'll break down this S in SI and SR. So SI is the amount that will be incurred by the direct insurance company, and SR will be the aggregate claim amount incurred by the reinsurance company. So what you will have here is, now instead of XS, you will write Y1 plus Y2. So we have YIs and we'll have ZIs. And this will go up until YN. And here you will have Z1 plus Z2 up until Zn. All right. So let us first try to look at the easiest case, which is the proportional reinsurance case. Okay, so let us say there is some alpha proportion which is kept by the ceding company. So again, I have alpha y and I'll have 1 minus alpha z. So not exactly right. It will be alpha x and 1 minus alpha x. So this will be z and this will be y. Does everyone agree with what I have written on the board? And this would be true for each one of these, right? Okay. So now if I have to try and figure out my SI for the, so what is my SI for? It is for the direct insurance company. So I'll just write my SI here. And what will it be? Again, Y1 plus Y2 up until YN, right? So if I take my expectation of SI, what will that be? Would anyone want to try? So basically I have to figure out expectation of Y1 plus Y2 up until Yn. How can I rewrite this as? Anyone?
Expectation of alpha x1 plus alpha x2 plus alpha x.
Exactly, Mihir. So I'll write it as, so I know that I can rewrite my Y1 as alpha x1, right? So what will be my Y1 here? Alpha x1 plus alpha x2 for Y2, and it will go on till alpha xn for Yn. So now I know that my alpha is just a constant. So I'll take that outside as common, and within the brackets, I'll have x1 plus x2 up until xn. And again, how can I rewrite this thing? Anvaya, can you help me with this? How can I rewrite expectation of x1 plus x2 up until xn?
n into expectation of x I.
Will it be n into expectation of, okay, yeah, I mean, yeah, it will be expectation of n into expectation of x, but the very first step would be that I will just rewrite this sum, which is exactly this, which is s. So it will be expectation of s, right? And then I can use the fact that my expectation of s is nothing but expectation of n times. So this should be capital N. It's that. But again, I'm not going to do that here. It's really basic. So, okay. So the next thing that we should try to do is variance. And it would still use, the same thing. And let's say if you try to do this now for the reinsurance company, what will you have? Let's say expectation of SR. What will it be? So similarly, instead of alpha, you would have 1 minus alpha. So it will be 1 minus alpha times expectation of S. Is this clear to everyone? So again, you can also see that, instead of just writing the expectation, even my SI. So I can rewrite this thing as alpha times x1 plus till alpha times xn. So even this would be just alpha times s. So what is my SI here? My SI is just alpha times s, right? And so would your SR be. So your SR similarly will also be 1 minus alpha times s. And then also you can take the expectation and everything else. So you will get the same answer. So yeah, in proportional case use it's very easy, right? Because alpha is just a constant and it really does not meddle with the expectation and variance that you're trying to care about. But again, let us try to see what happens with the MGF. MGF is interesting. So let us say now I have MGF. So I have to write, let's say MYT. How can I rewrite this thing as now? Anyone? So I'm just writing this for one of these, and then you can sum it up and do the whole sum multiplication thing that all. But again, I'm just caring about this one y right now. So if I have to figure out MYT, again I can rewrite this as expectation of e raised to py, right? How can I rewrite this thing as now? Given that I know that my yi is alpha xi. Anyone?
So it will be expected value of e raised to t into alpha times x, right?
Exactly. Yeah. So it will be t alpha x. So now again, remember, always try to see if you can work with the information that you already have and figure out something that you want to know. So now I want to know something about MYT, but I only know the distribution of x. I do not know the distribution of y as of now. So I cannot simply figure out MYT until and unless maybe I figure out the distribution of y or else I derive it somehow, right? So what I can do here now is, because my alpha is just a constant, I'll put a bracket here. So this can become my mx, and now instead of t, I have t times alpha, right? And I do know my mxt because I will know the distribution that my x follows, right? And instead of t, you will just substitute t times alpha to get m by t. Does this make sense? Do let me know if you have any confusion with what I just wrote on the board. Any doubts? So again, I have just used the fact that, my alpha is just a constant. Does this make sense to everyone? Yes or no?
Yes, ma'am.
Thank you.
Yes, ma'am.
What about others? Okay, so basically, if you are looking at the proportional reinsurance case, it's very easy because it's just alpha and it doesn't really change much because alpha is also a constant. So what would make this really complicated is if your alpha would differ with each of these i's. So let's say if you have alpha I here instead of a common alpha, then it would be a bit trickier. But again, alpha is just a constant, so it would just be tedious. So, but we don't have that, so you don't have to worry about that. And the next kind of reinsurance treaty that we studied was excess of loss reinsurance, right? So let us say if you have excess of loss reinsurance in place, so just reminding ourselves, if let's say my retention limit is M here, so what will be my distribution of Y and what will be my distribution of Z? Anyone? Yeah, what should I put here, 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 and here? Come on, first. This really shouldn't take time. What should I write here?
It's
X here,
M
here,
0
correct, and
x
here.
minus M.
Thank you very much. Yeah, so we have this. And again, just a different notation, which would be, a very nice, short and crisp notation for this two distributions. You can also write this as where yi is just a minimum of xi and m. So again, you can choose to ignore these i's, but you can also write these i's because again, what we care about is the aggregate claim amounts. And we do have y1, y2 up until yn. So if you write y, that would just be a generalized version and it's not a big deal, I would say. So what you have is a minimum of xi or m, right? So if your actual claim amount is greater than m, then you know that yi will only be m. Because if your this exceeds m, then y only pays m, nothing more than m. And similarly for z, you can write it as maximum of, would anyone want to guess what would this be maximum of? So my y was the minimum of x and m. And what would be my z maximum of? Anyone? So try to think of two cases, I would say. Anyone? I mean, I've already given the crux of the answer. There's nothing left really. But I see that you guys are already just waiting for the lecture to get over. Okay, so it would just be maximum of 0 and xi minus m, right? So let us say if there is a claim amount x which is less than m, then you know that, this is going to be a negative number, because if x is less than m, x minus m will be less than 0, and therefore maximum between 0 and something which is less than 0 will just be 0, right? And that is what the reinsurer company pays. And let's say if your x is greater than m, then you know that x minus m will be greater than 0, and between 0 and a positive number you would always go with this number, and that would be exactly what the reinsurance company will have to incur. So this was just a bit of, you do not necessarily have to use this somewhere, but yeah, just something to think about. So I guess that's all for today. I can see you guys are just waiting. So let us keep a lecture tomorrow as well, I would say.